Right. So good morning, good afternoon, good evening, everyone. I think everyone is coming from different parts of the world. And today we have this webinar and slash tutorial called Low-Cost Photogrammetry for the Method Documentation of Cultural Heritage. This webinar is organized by the ISPRS Commission 2 Photogrammetry and especially the Working Group 6, Cultural Heritage document data acquisition and processing. And we also collaborate with CIPA Heritage Documentation Emerging Professionals, which is more or less the youth branch of CIPA, to organize this webinar. So it's my pleasure to welcome all of you for this 3-hour online webinar and tutorial. So the way that this will work is that we will divide this into 3 parts. So the first part will be a presentation by Francesca Matrone about the theory of photogrammetry. And then we will show you a demonstration of a open source photogrammetry software by Susana Del Pozo. And finally, some tutorial regarding 3D editing demo. So what you do with the data that you get from photogrammetry by Alessio Ferroni. So I suppose we can start right away. And I would like to introduce the first speaker, Francesca. So Francesca is currently assistant professor in the Geomatics Laboratory in the Polytechnico di Torino in Italy. Her research focuses on deep learning techniques for geospatial data, point clouds, scene understanding, and semantic labeling. And she has been working with a lot of tasks regarding 3D city models, particularly scan to BIM. I know that she works a lot in that regard, and also point cloud registration. She is also the main promoter of the ARCH dataset, the Architectural Cultural Heritage dataset of point clouds, which was designed for the semantic segmentation of built heritage point clouds. She was also a visiting researcher at MIT and at INSA Strasbourg in France. She is currently the secretary of the ISPRS Working Group 2 of the Commission 2, also Commission 2 regarding photogrammetry, and Working Group 2 regarding point cloud generation and processing, and is a member of the Italian Society for Photogrammetry and Topography. So with that, I would like to invite Francesca to share your screen and start your presentation. The floor is yours.
Yes, thank you. Let me share my screen. Okay, can you see my presentation? Yes?
Yes,
No?
yes, we can see.
Okay, perfect. So, hello everyone. This is what we are going to see in this first part of our webinar today. So we will have a really quick and brief theoretical background on photogrammetry. We will understand how it is working, the processing workflow, the data acquisition strategies, some existing open source software, and then the low-cost sensors. And we will conclude with the newest developments and some future perspectives. So first of all, I think that all of you know what photogrammetry is, of course. So I will not go through this definition, but just to highlight and point out that it is useful to obtain for us reliable information and to allow us to extract information from images and to have the possibility also to measure and interpret our results. So, okay. So from the photogrammetry, what we are able to do is to detect any kind of objects with any shape and size. The other important thing is that we are able to detect and survey objects that are difficult or completely inaccessible. So if you just think about like the survey with drones, you can go wherever you want and also survey, of course, parts that are not possible to be accessed otherwise. and also the detection of objects that actually could be accessible, but maybe for a limited amount of time. We will see in the next slide a case study, for example, where, sorry, can you see the correct presentation? Because I cannot see my sharing of the screen.
Currently, I see photogrammetry is the science of obtaining reliable information and so on.
Okay, okay, perfect. Not the presenter view.
No.
No.
Okay, sorry, it's just because I couldn't see it. Okay, and then, so limited amount of time, just because you can think about, for example, cultural heritage may be damaged for an earthquake or some other natural event. That could be the use of also, in that case, photogrammetry. So the objective of the photogrammetry is to reconstruct the reconstruction of a georeference, which is quite important, but also metrically accurate 3D models. And we are going to perform different kinds of measurement. The geometry is the most important one, but also on, for example, radiometry, so the radiometric component. This thing will allow us to carry out different kind of analysis. For example, so the structural ones for, I don't know, historical structures, historical cultural heritage, and so on, but also digital twin, for example, it will allow us to perform the scan to beam processes and so on, for restoration purposes, for decay, mapping, and so on. So just to let you see where we are, what is our contest, we are in the 3D measurement. So we are here, no contact techniques, optical part with light, and then we are here, so photogrammetry. Just to have a really brief introduction to some theoretical part of the photogrammetry, we can say that acquiring an image, it means to create a 2D representation of course, our three-dimensional world, so our real world. We can think that with the most simple approximation, an image that we are going to acquire in our photogrammetric process is a central projection. So we have, as you can see here, we have the lens. We then have our reality. The characteristic of the camera give us the field of view, that is this part, and each point on the reality is then back projected or reprojected in the sensor. So why this is a central projection? Because there is a projection ray that connects the reality, so what we see, to into our 2D image. So as you can see here, we have, okay, we have our projection axis and our projection ray. They both start from C. C is the center of our camera. And then we have two different points. This one, which is P in uppercase, which is the point on our real object. So the point in the real world. And then, and then we have the point, which is the projection in our image plane. So point in reality that is back projected here through this projection ray into our camera center. What we have to take into account is that P, of course, has some 3D, it is a 3D object point, so it has three different coordinates. Then we have P, which has 2D, it is a 2D image point, so it has other coordinates, which in this case are Xi and Eta. And then we have C, so the camera center with our other coordinates. Then we have the camera reference system, but also the world reference system, of course. So the reference system where our object is placed. Oh, sorry. And then we also have our image reference system. So you can see how it is going to be complicated, this photogrammetric process. But the most important thing, it is that P in the capital letter, P in lowercase, and C, they are aligned on the same projection ray. So all the points that are on this line, we can see that there is the principle of collinearity, which is like the heart, the core part of our photogrammetry, and we will see in a while why. The other important thing, it is the focal length, which is the distance that we have from the center point of our camera and the image plane, okay? So now, given our camera center, which is C, and our projection axis, this one, as you can see, we had before called projection ray, but now we have seen that everything is on the same line, which is, so it is, there is collinearity, and we decided to call it collinearity ray. So here, given our camera center and a projection axis, for each object point, so P, the perspective image, this P, so the blue one, is formed by the intersection that we have between our collinearity ray, so from C to P, and of course our image plane. And this condition is expressed in the collinearity equation. So don't worry, I will not go really through to this equation, but it is just to let you understand that this is really the core of the photogrammetry. And what we have here in this equation, we have different elements. So we have X, Y, and Z, as you can see here, that are the coordinates of the real coordinates, the coordinates in the real world. Then we have C and eta, which are the image coordinates. We have some R that we are going to see in a while, that are some elements of a rotation matrix, and I'm going to explain to you why. Then we have C and eta 0, these two, that are the image coordinates of our principal point. C, of course, that is our focal length, as you can see from the slide. And then we still have X with 0, Y, and Z, which are the real coordinates of our point that has been captured. So the camera center, and then our the rotation elements. So as you can see here, we have these R. It is a rotation matrix, and it is expressing the rotation of our camera. So as you can see in this small image, of course, our camera can rotate in the space. So we need to include into our collinearity equation some parameters, some elements that are able to express and to represent this rotation. This rotation is, as you can see here, omega phi and kappa, or also the yaw, pitch, and roll. So the rotation along our three axes. Another problem that we have to consider when dealing with the photogrammetry is that the center of the image sometimes does not correspond to the optical of the camera, so the center of the camera. Why? Because they are mechanically constructed. So of course we could have this misalignment, but also this parameter is one thing that we have to take into account. Just keep in mind that, as you can see here, for each P point that we have in our real world, we have two collinearity equations, because of course we need the two image coordinates. Now, we can also measure, accurately measure with high precision our angles, so the vertical and horizontal, in order to detect our P. But the important thing here that I want to highlight in this slide is that if we only have one image, we cannot understand if this P point is here, it is here, 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 or here, because it could be everywhere or in each position, very different position in our projection ray. So the important thing is that in order to define correctly the position of P, what we need is to have another camera. Pay attention that this is not a stereo camera. This is just a single camera that is moving. So I'm acquiring one image and then I'm moving from another camera center, I'm acquiring another image. In this way, moving the camera center, I will have two different collinearity ray, and I will be able to correctly detect where my point is. In this case, we are dealing with the structure from motion, as you can see in the right part of the slide. So is the technique that actually we use today. So we acquire, I don't know, with the drones or for the terrestrial photogrammetry, what you usually use, we acquire the images from different positions, and then so the camera, it is moving over time, and then we put everything together. So this is structure from motion, and these are the principles that are at the base of the structure from motion. As you can see from this video, so just to recap, the necessary condition to establish the position in the space, so in the 3D space of any object starting from our image coordinates, is to have at least two images taken from two different points of view. Here you can see that there are some different approaches, models, sorry. So the single view geometry, the two view geometry, which is actually a stereoscopic model, and what we are going to use. So the multi-view geometry, the base for our structure from motion. Now, when we are dealing with the processing, so you will also see this part in the practical part with Susana. In order to extract our 3D coordinates of points in our pay attention object reference system, what we need to know is the position, but also the orientation of our camera during our acquisition phase, and also the characteristic of the camera that are able to define our image reference system. So on one side, we have the object reference system, and on the other, we have our image reference system. So now we are dealing with two different orientations. And these two different orientations are giving in our photogrammetric pipeline, we will see in the next slide, two different results, two different products. So as regard the interior orientation, it concerns a set of parameters that allow you to reconstruct the metric of the central projection. They are the same for all the images that we acquire because they are linked to the camera. And of course, the camera, it is always the same during our acquisition. And this set of parameters is provided usually by the camera manufacturer in special documents that are our calibration certificates. Then in this interior orientation, we have to define the image reference system. So the parameters that we have to define are, as you can see here, the xi and eta with 0, so the coordinates of the principal point, and c, which is our focal length. Then we move to the external orientation. So once we have set the information of the camera, we move to the external orientation, which is divided into relative and absolute. The external orientation is the set of parameters that is useful for defining the spatial arrangement of our camera, so its movement, with respect to a certain 3D coordinate system. So it is defining essentially the spatial position of our camera in our 3D space. How can we define it? Through 6 parameters, which are 3 translation, of course, and 3 rotation, and are exactly those that you can see here. Then we move to the relative, so we can split our external orientation into 2 parts. So in the relative orientation, we determine the relative position of, for example, 2 images, so which is the position of these 2 images, creating the projection, the intersection, and the projecting rays that we saw before. Therefore, we can start creating the 3D model of our object, but pay attention still on an arbitrary scale and with a generic spatial position. So it is independent from our world reference system. Once we have this part, so we have performed the relative orientation, that is, sorry, I forgot to show the image, which is this one, where we set the position of the images, we move to the absolute orientation. In this case, the model obtained in the previous phase, so in our relative orientation, is roto-translated and scaled in order to refer it to our absolute reference system. How can we do it? Thanks to the ground control point or some targets that are those that you are going to column to indicate in the software of photogrammetry during the photogrammetric pipeline. Here you can see our collinearity equation of before. Just to let you understand, this is just written in a different way, but that we can see all these parameters inside. So the coordinates of the object point, which are the red parameters, the interior orientation parameters, the green, and the external orientation parameters that are the blue. So this is, again, why it is so important to understand the collinearity equation. So here you can see the relative orientation from the infinite possibility that we have to place our 3D point. We find the unique and correct one, and we start to build our 3D model. Then we scale it, we roto-translate it, and we place it in the real world, and we are performing our absolute orientation. So this is the pipeline of the photogrammetric process, the one that you are going to do in the practical part. You always start with 3 different phases. So the data acquisition, the camera orientation, and the model restitution. The important thing is that what I told you before, so in the first part here, you're dealing with the relative orientation, and you are generating, so you are aligning your images, and is this part of the photogrammetric pipeline when you are generating your sparse point cloud. Then you move on to the bundle block adjustment. You perform the GCP, the ground control point collimation. You create the dense cloud. So you are going through your absolute orientation. And then finally, what you export, you can process it, post-process it, and work on it on CloudCompare or any other software. So this is the principle of the structure from motion, what we use actually like every day when we deal with this data. There are different steps. So as I showed you before, the first one is the feature extraction. So the common points from one image and the other. And these blue points are those that are used in the sparse point cloud. Here we can see the feature matching. And finally, the bundle block adjustment, where through our ground control point, we are able to define our dense point cloud. Here, there is an example. So from the sparse point cloud, the dense point cloud, the images that you can see in the top part that have been aligned, and finally the mesh. So just take into account that there are some different source of errors. We have different causes of distortion when we are dealing with our cameras and with our images. I will not go through all the theoretical part of this, otherwise I will just go too long, but just to let you understand that we have some distortion that could be due to the camera, to the sensor, to the lens system, and for example, regarding the sensor, to the problem that the ideal sensor has square pixel, but actually in the real one, we do not have square pixels, perpendicular row and columns, but in the actual one, in the real one, they are not. But the important thing is that actually they are considered constant, and we can model them through the we can model and adjust them through our calibration. That it is always, as you can see here, it is performed in the software for our photogrammetric processing. This is another example about the radial distortion. We can solve it by our camera calibration through pre-calibration or self-calibration. Now, regarding some data acquisition strategies, here you can see that when we acquire the traditional type of acquisition is with an overlapping between our strips of transversal coverage and longitudinal one of 60% and 20% in order to create all the images together. I'll call our photogrammetric block. But we have to take into account that if we want to generate point clouds with based on the structure from motion, it is necessary to increase the coverage, both the longitudinal and the transversal coverage. So as you can see here, this is from terrestrial photogrammetry. And this on the right, it is the modern schema. So not anymore 60% in strips overlap and 20%, but 80%, 60%, as you can see here. So we will have, of course, more images in order to be able to see the point in a higher number of images. These are just some examples of some acquisition strategies, and other example of the control points. So here are target. They could also be some natural points, as you can see here. And if you are dealing with drone images, they could be natural points, like for example, corners or horizontal elements like in the city, but also pre-signalized ground control points. This is an example of a cultural heritage that was surveyed and monitored during an earthquake. So from the sparse point cloud, the dense point cloud, and the mesh, as you can see here. Here you can see the first damages of the earthquake, but then the other damages, you can see this part and here on the bell tower, and finally this is after the third earthquake that there was. This was a church in the center of Italy, damaged in the earthquake of 2016. So here you can see from the different epochs how it has changed and how also you can manage our photogrammetric products. Now to the last part, open source software. There are many of them. You are going to see GRAPHOS in the following part. Of course, there are others, like, for example, MicMap, ColMap, Visual SFM, and so on. There are others that are commercial. Just take into account, here you can see, I just forgot to tell, here you can see I leave the link and we will share this presentation, some best of free photogrammetric software with all the different specifications for each of them. Just take into account that when you want to choose from a commercial solution versus an open source, you have to think also about some of these elements. So, for example, the number of photos that you want to process. In some cases, with the open source solution, you cannot process many photos. The density of the results that you want to obtain, the accuracy, the possibility of cloud processing, the point cloud classification also possibility, so identify the classes, some saving option. When you are dealing with open source software, sometimes also the export file formats are reduced, and also the possibility of sharing. Then, as regards low-cost photogrammetry, it would be interesting to understand what would you define as low cost, because to me, I don't know, low cost could be like 40, 50 euros, maybe for Elon Musk, it could be, I don't know, 10,000 euros low cost photogrammetry. But here you can see that there are on the market many different options. So from the small one, which is the Raspberry, from other ones, they can be also compared. They have, of course, different results. And here I just wanted to show you an example that was carried out on a cultural heritage case study. The camera, it was this DJI Osmo. And here you can see the difference. So on the right, you have the image acquired with the Osmo, and on the left, those acquired with a reflex camera. So you can understand, especially from this part, that not always the fact that we are using low-cost photogrammetry, it means that the result, it could be worse. In some cases, it could be even better. It always depends on what we want to work on. Here, this is another comparison. So in the upper part with the reflex, in the lower part with the DJI Osmo, and you can see some differences of in the meshes. And here, a detailed part of these meshes, the zoom part. Here is with the LiDAR. This is the noise of our point cloud that has been generated. The texture model. LiDAR, reflex, and the digital camera, and our low-cost sensor. So you can see that actually it is quite good as a result. Of course, we have to think that there will be always, when we are dealing with low-cost photogrammetry, there will be always some drawbacks. In this case, for example, short battery life, reduced angle of sight, and so on. We will have to take into account many different parameters, like, for example, shooting distance, lighting condition, and so on. These are important factors that can influence the quality of our 3D models, but we have many advantages. So, for example, the speed in the image or video acquisition, its user-friendliness, the functionality, the lightweight, the price, and also the fact that the rich detail is very competitive if compared to the other camera, as well as the metric accuracy. So I can tell that these solutions are really effective solutions, especially for the rapid mapping. This is just another idea, also with low-cost cameras, so spherical photogrammetry. That, just to let you know, that could also be applied in underwater scenarios. So this one was me underwater, just taking these pictures, and could also be applied. I just didn't, I couldn't add the images here because it is still an ongoing project, but could also be applied on underwater cultural heritage, and it has already been done. So to conclude the last 2 minutes, new developments and the future perspective. As you all know, I think now we are dealing with artificial intelligence. When we have the products of our photogrammetric pipeline, so with our point clouds, we can do plenty of tasks, a lot of them. One of them is the semantic segmentation. So this is a point cloud entirely acquired through photogrammetry, both terrestrial and also part, the top part with drones. And it has been semantic segmented. Why it could be useful? This is another one with both machine learning and deep learning algorithm. Why it could be useful? For example, this is just a hint, but there could be many others, because we can help the scan-to-beam processes or any other digitization processes of our cultural heritage. This is another example, always performed with artificial intelligence algorithm. So a 2D automatic restitution from an ortho image of 2D CAD drawings. So this is the ground truth, and this is the predicted drawings, as you can see. Another work, always on cultural heritage and artificial intelligence and photogrammetry, so everything together. It could be to reconstruct, for example, the lost heritage, something that we do not have, but maybe we have videos, we have historical images. And here you can see that it has been reconstructed, always with artificial intelligence. And finally, as you know, the use of NERF. NERF stands for neural radiance field. They became more widespread in the last years. We still have some problems when we are using them on cultural heritage. We could have problems on the geometric precision, of noisiness, on the density of the point cloud, which is really heterogeneous. But since the developments are really going on really, really fast, just think about the possibility of the data completion that we can have if maybe we weren't able to acquire a certain part of maybe it was inaccessible or something else of our element, and the automatization of the process. So these will be continuously getting better and better. Just some future perspective to conclude. We can say from what we've seen, from also my experience, that low-cost photogrammetry is going down a really, really promising path. And also you can consider the spherical photogrammetry and the 360 cameras for us, for example, a rapid solution for rapid mapping and any other things, also for cultural heritage. That in the last years, the acquisition strategies are becoming increasingly simplified and automatic, making the photogrammetry more user-friendly and more suitable, also with the low-cost sensor. So then that the open source software has improved significantly in the recent years, and they can ensure comparable, I put an asterisk because they are actually really good results, but always pay attention to what you want to obtain if you want to compare with the commercial ones. And also that artificial intelligence is taking the lead both in the acquisition, in the processing, but especially in the post-processing of our point cloud, both from photogrammetry or any other techniques. So thank you. I finished. I just took 5 minutes more. I'm sorry.
No, actually, it's you are on time because I was
Okay.
a little bit early when introducing you. Thank you very much, Francesca. That was very interesting. Lots of people seems to like your slides, and they were asking if you will be willing to share them later. Yeah, so maybe we can go to some questions. So I see that there are actually some questions already in the Q&A section, some questions also in the chat. I will try to curate them, and maybe if we have time, we will be able to answer all of them, but let's see if we have enough
Or
time.
I can also answer later. It is.
Of course, yes, because you can also answer directly in the Q&A section. So let's see. I think this question is quite interesting. I would like to know your professional opinion about the use of LiDAR on Apple devices. Can it be useful despite its limitations? Thank you in advance.
I didn't use it, but I know that some colleague of mine have used it. We have tested it on especially some cultural heritage elements. We have seen that actually it is working quite good, but the problem is that sometimes the accuracy that you have is not so good. Especially in some part of the point cloud. So I still would, and it is also it also depends on the acquisition strategy that you are following. So we have tried different acquisition path, and we've seen that actually it is quite good, that Apple LiDAR, so the LiDAR of the Apple. So I would say that I still don't know, I still have some doubts for the cultural heritage, but for other parts, when you maybe do not need a really high accuracy, or if you need it for like virtual reality or for dissemination and communication purposes, yes, it is a really good instrument and possibility.
Thank you, Francesca. I think Maxence Balif, he also said that from personal experience, iPhone LiDAR is good for small areas, about 5 meters. Otherwise, there is a big drift. So thank you for that. So it's totally interesting to share the experiences.
Yeah, I just forgot to tell, but yes, of course, I was thinking about like small objects, not, of course.
Naturally.
We have tried also for example, rooms, but if it is still not working, so. I'm just seeing a question that I wanted to answer.
Of course, go ahead. Which one?
Caroline, I don't know the pronunciation, Machado, I don't know. She's asking, when you make a survey of, for example, a castle using a camera drone, is it enough to plan flights only in the horizontal direction above the castle? I don't know what you mean with horizontal, if you are like the vertical position is through the pointing through the ground or to your castle. Usually when we are working, especially with cultural heritage, but also in other cases, we plan different stripes. So some of them natural, but other with the camera incline of 45 degrees, just as you were mentioning, to be able to acquire also the facade and the other elements. Just take into account that, for example, the part, if you have a facade and the part from, I don't know, just below the roof, it could be in that case that you are not able to acquire those points, even if you are using a 45 degrees orientation of your camera. But yes, it is the proper way to acquire the data, not using only the nadir images, but also the oblique flights.
Thank you, Francesca. I see one question that I think comes up very often, and I guess it would be nice if we can answer it. Hi, can we use cell phone camera to do good photogrammetry?
Can we?
Use cell phone camera.
I could say that I've never tried it. So it depends. Here I've seen good photogrammetry, what you intend for good photogrammetry, what you mean. Because if for you good photogrammetry is just having your 3D model without checking like the accuracy, the residuals, and so on, I could say yes, more or less like the LiDAR of the Apple devices. But then if you instead, if you are dealing with other engineering processes in results that could be suitable for engineering purposes and so on, I have never tried it. So if anyone else has like experience, yes, you can just intervene and tell. But I would say that it depends still on the purposes and the aim of your 3D model that you want to generate. But then we have really, really good cameras now with the last smartphone that are on the commercial that are on the market. So I think that in the next years or in the next year, just we will be able to have and obtain really, really good results also with our smartphone. Also
Okay.
from the accuracy point of view.
Yeah, thank you. And actually, this question is a little bit similar. Not the same, but there is also a question regarding the use of 360 panoramas, especially obtained using the Matterport 3D camera. I don't know if you're familiar with that.
I've never used it, so I can.
Mm-hmm.
I don't know, Arnadi, have you ever tried?
Not precisely with that model, but I know that with 360 cameras, the one that you also presented before, you can also create this even using open source software, I guess.
Yes, but I've never tried it. So with those images, I've always used like Pix4D or Metashape. So I haven't tried, but we can.
A very good question that I have here is which commercial and which free photogrammetric software do you recommend?
Oh, I just told it. I use commercial, Metashape, and Pix4D. I've also tried context capture from Bentley System, but I moved to the other two. And then for the open one, I've tried Visual SFM and Micmac. And I've seen that, for example, I made a comparison between Visual SFM and it was Metashape for the cultural heritage, the roof elements of a church. And actually what I've seen, what emerged is that Visual SFM had a higher density in the point cloud of those roofs. So in that case, it was even better than, but it was like 2 or 3 years ago. In that case, it was even better than Metashape. So what I would like to highlight is that using open source software it doesn't mean necessarily that your result will be worse. You just have to take into account those elements that I put in the slide, like the number of images and so on, that maybe you can have some limitation, but sometimes the results could be really good. Also with Micmac.
Very nice. I think we still have some time, so I will read you another question. I guess this is also an interesting question. It's more on the basics, on the theoretical side. So what is the difference between modeled photogrammetry rather than a simple aerial drone photo? So I guess that's also interesting to know. What would be the difference, if you do photogrammetry and not?
But model photogrammetry is the one from terrestrial, just to understand.
So the way I understand it, I think it's correct me if I'm wrong, but the question may be related to what would be the advantage of applying photogrammetry on, let's say, aerial images instead of just aerial images on themselves. if for practical use.
I still have do not understand the difference. Try
That's what I
again,
mean.
Arnadi, if you have
But I
understood the
guess,
question.
I mean, I may misunderstood also. So if the one who came up with this question can maybe,
yeah, or if the authors would like to specify.
Yeah. So that would be great. In that case, this is more of a technical question. Hi, you showed an image of an ortho image to an AutoCAD drawing. Is this done in any software or drawn manually in AutoCAD with the ortho image as a reference base?
Okay, so that work, it was presented in June in CIPA that we had in Florence. So it is really, really new. And it is not done implemented in any software. So that one, it was the neural network were able to recognize the pattern of the texture and the stones and the wall. And so the ground truth, it was manually drawn in AutoCAD. And then with, of course, the ortho image as a reference. But then the other, it was not still implemented in AutoCAD, but just the result of the artificial intelligence algorithms. So the results, of course, just to add a thing, the result, of course, it was used, that it can be used into AutoCAD, but it is still not implemented, that pipeline.
Okay, I think we still have time maybe for two small questions. I will just read some short questions, and I think this one is also interesting. Would the diversity of cameras affect photogrammetry?
Okay, everything depends on, also in this case, what with diversity of camera, what you mean. So if you are dealing with low-cost cameras and other cameras, or if you're dealing with just like camera with similar parameters, like for example, similar number of similar resolution, sorry, or other parameters, in that case, no. But what is important when you are when you think about the results that you get, it is the model of the camera, yes, so the parameters that you have, the resolution and so on, but also, and especially, I would like to highlight this thing, the acquisition that you perform. So if the acquisition, it is properly carried out, you have enough images with the good resolution, you have the good distance, good distribution of images, so the correct stripes, many inclination, both with drones, so with terrestrial photogrammetry and so on. In that case, you can obtain, and also you have good accuracy in the ground control point, or in the point that you use in the bundle block adjustment. In that case, there is no much difference from one camera and the other, if of course we are talking more or less of similar sensor. Then if we are dealing with a smartphone and the best reflex in the world, in that case, something would always change.
Maybe a last quick question, Francesca. Someone wanted to know what tools do you use for point cloud segmentation?
The image that I show with the point cloud semantic segmentation, that one. Okay, okay, that part, it was mainly done with Python. So it was a neural network, the DGCNN in particular. It was a neural network directly, where in Python we directly input the point cloud, but with the software you can also do it. So it depends on the class that you're working on. In the case that you've seen in my images, so in the context of cultural heritage, those classes that we need, the categories that we need for the cultural heritage are still not implemented in some software. So you have seen, for example, that we had columns, we had vaults, we had stairs, so a higher level of detail that where the commercial software are not dealing with yet. That's why we worked both with random forest or deep neural networks on Python. There are other more general classes, like, for example, vegetation, roads, buildings, or also vegetation. You can divide it into low vegetation, medium vegetation, high vegetation, ground points, and so on. In that case, you can use some software. Pix4D, Metashape, when you create your point clouds, are already able to do it. The one of Metashape, it is working quite well. Otherwise, we also use, for example, eCognition, which is another software. But eCognition, you are not going to create your point cloud there. You are just going to use your those algorithms to work on your point cloud. So this is the difference with, for example, Metashape, where you create your point cloud, then there is the possibility to choose the segmentation, the semantic segmentation, so the classification of our point cloud. I hope I've answered the question.
Thank you very much, Francesca. I mean, there are still some questions in the Q&A function. So if you have the time, then we'll be very grateful if you can take a look at them and maybe answer them in text.
Yes, I also want to answer to the one of before that I wasn't able to answer. So I hope he or she has written something else. So I will go through them.
Sounds good. Because right now I think we will have to move on to the next presenter. I will quickly introduce you to our next speaker. So our next speaker, who will be showing us a demonstration and a sort of tutorial on how to use the software GRAPHOS, which is an open source photogrammetry software, is Susana Del Pozo, who is currently assistant professor in the Cartographic and Terrain Engineering Department at the University of Salamanca in Spain. Her research focuses on computer vision and photogrammetry, as well as radiometric and geometric calibration, and she also conducts studies regarding multispectral and multi-platform problems. She is an active member of the TDOC research group in Spain, specializing in information technologies for the intelligent digitalization of objects and processes. And she is actually the chair of Working Group 6 of Commission 2 of the ISPRS, Cultural Heritage Data Acquisition and Processing, which also organizes this webinar that we are all attending right now. So with that introduction, Susana, are you ready with your slides? Or
yes, I'm ready. I'm going to share my screen.
And you can try sharing your screen now.
Let me know if you see the screen.
Yes, we can see it. I can see it. So okay, so the floor is yours, Susana.
Many thanks. So hello everyone. First of all, I want to express my gratitude to the organizers of the event who have made this event possible. And of course, a really welcome to all the attendees that are interested in this webinar. I hope you will find this session useful. And as Arnadi introduced, this is the second part of the webinar that deals with the initial practical part of the webinar. It is titled Photogrammetry Demo. And in this part, I will present the potential of the GRAPHOS software. Well, here, summarize of the agenda of the next 45 minutes, give a software introduction to GRAPHOS software, the key features and the problems it seeks to address. Then I will guide you on how to access and install GRAPHOS. And finally, I will showcase GRAPHOS in action, okay? Well, first of all, GRAPHOS is the acronym of Integrated Photogrammetry Suite. And why GRAPHOS be of interest to you? Well, it is designed to be accessible to everyone, and it is completely open source. So in this way, it has no financial barriers. It also offers an intuitive and user-friendly interface. So it doesn't matter if you are or not expert in the photogrammetric reconstruction process. The software leverages a structured from motion technique, as you can see in the previous section. So give automation to the photogrammetric process with any type of image and camera, and without the need of previously knowing the geometric calibration of them. Unlike many other solutions, it results of our in-house development. So in this way, this gives us full control and allow us to tailor its capabilities to our needs. And finally, I would like to highlight that behind GRAPHOS are two leading institutions, the University of Salamanca and the FBK in Italy, and that its development was possible thanks to an ISPRS scientific initiative. Regarding the methodology and the workflow implemented, is close to most of the software that deal with the photogrammetric reconstruction. Also, the licenses software. First, we're starting with loading data that could be both images in this case and also videos. Is a novelty. Also, in this step, we could import the camera calibration if we have it, and also the RTK data, also if we have them. Then we continue with the feature extraction and feature matching. After that, we start. I wanted to say that the feature extraction and feature matching sometimes is not. It's an opaque method, and we only have the possibility to push the button orientation, and in this way we have a total control of the feature extraction, and also then, of course, we continue with the orientation itself. That solves both the position of the cameras and its calibration in case we don't have it previously. Also, in case we have RTK data, here we will be use it. If the images have GPS data in the EXIF, this data will be used for this process, and otherwise we can get a relative orientation. After this process, we will obtain the sparse 3D model and the camera locations. And we can see, we can move this model and see these camera locations. Then we can, in this step, we can introduce the ground control points if we have them in order to improve the results and avoid errors or big errors, okay? And next, we continue with the densification of the 3D model after we get the dense 3D model. Finally, we make the mesh process to obtain the 3D texture mesh model. You see that there is no, in this methodology or workflow, we don't have implemented yet the orthomosaic and the MDT model, okay? But we have developed, but it's not implemented in this version. Okay, regarding, just in this slide, show you the core of GRAPHOS regarding the algorithms and quality control tools implemented. Regarding the feature extraction, the SIF detector and the descriptor are implemented. In case we have CUDA support, the SIF GPU library is run, and otherwise OpenCV is run. After this process, we could see the key points detected in order to control them with the viewer. Regarding the futures matching, again, SIF GPU is implemented, and in this case with a robust matching strategy that includes a ratio test, cross-matching, geometry test, and ransack adjustment. Again, after this process, we could check the matching results thanks to a viewer. For the orientation and self-calibration, the call map library is implemented. And then for the densification process, 3 algorithms are available. Even the first one is the recommended OpenMVS, because with this, we obtain the best results. We can select which one we wanted in each case, okay? And this process involves 3 stages: the distortion correction of the images, the calculation of the depth maps, and the fusion of these maps. And finally, for the meshing process, the Poisson surface reconstruction is implemented. Regarding the access to the software, you can find it at this GitHub repository that I could go to this. This is the repository, and going to the release button, you can get the last version of the software, okay? It's a beta version, so it's not the final version. We think that in January have the established version with the manual, and also with the ortho mosaic, and also with the DTM model implemented. So you can find here the last version we have. This is from yesterday, okay? So here you can find the software. Just click in and download the point X, okay? Okay, I'm going to cancel it because I have it. Okay. And regarding the operating system and the system requirements in general, GRAPHOS is compatible with Windows 10 and 11, both 64-bit versions. Regarding the CPU, we recommend a 4-core Intel or AMD processor with a clock speed of 2.0 gigahertz or higher. And this will ensure, in this case, that the software can efficiently process complex tasks, okay? Regarding random access memory, a minimum of 16 gigabytes of RAM memory. And regarding graphic processing unit, we recommend CUDA support, compatible with GPU minimum of the version 3.5. Okay, and with this toolkit and drivers. Otherwise, as I mentioned before, it will proceed but slow down. Regarding the installation, you will probably get a warning that it's not a secure software. Just let's run anyway and continue, okay? And it allows you to select between 2 languages, as you see, Spanish or English. And well, the rest is the normal installation process of any software. Just indicate the path where it will be hosted. If you want a complete, compact, or custom installation, by default is the complete one, the full installation. And if you want to create a folder for this software. And finally, the issue of whether or not to create a desktop shortcut as the main software. And now let's move on to the live demo. In this slide, I present the interface of GRAPHOS and just present the main parts of the interface before I start the demo. In this first menu bar, we have some options like File, View, Workflow, Tools, Plugins, and Help. Let's say that only plugins and help have still don't have functionality. Okay, we don't have yet the manual, and also the plugins are not implemented in this button. Then we can find some panels that offer graphic or alphanumeric information. The project panel, where input and results will be stored in hierarchical way. Then the thumbnails panel, that where images or frames of the video, in case we input, we import a video, will be seen in miniature. The console panel that will inform us of the progress of the process and also the results of interest. The properties panel that will show the metadata contained in the EXIF of the images, so the name of the camera, resolution, if it has GPS information, etc. And finally, the main panel where the results will be displayed in 3D, okay? We can move, interactively move the models. Also, we can make some settings like make more bigger the points, okay, of the sparse and the dense 3D model. Before starting the live demo, just let me show you the 5 reconstruction sample I would like to show you today, if we have time. That I hope so. I will show you 5 projects. The first one, well, the three of them regarding different cultural heritage assets, whose 3D model was a relative model without the scale. Okay. The first one is a chart, and mainly the main entrance door of a chart. The second one are the ruins of a chart, and the third one is like a kind of chart altarpiece. Okay. In this case, it is from a video, and we process 43 frames. I don't mention, but in the previous case, 53 images, and in the first case, 4 images. Okay. Then a cultural heritage sample that is an entire chart acquired with a drone acquisition, where we can obtain the 3D absolute model of this chart, since we have the camera GPS data. In this case, 105 images are processed. And finally, an urban environment acquired with drone, in this case 15 images, and without GPS information, but we have ground control points acquired in situ with the help of some targets established in this environment. Okay, so let's start with the first one. Let's move to the software. So we open GRAPHOS. Can you see my screen? I hope so. Okay. So the first step is to create, let's say, the project, or open a project if you have one previously saved. Okay. You see only these 2 buttons, open or create a new project or open a project, and also you can have available the setting button. In the setting button, you have only like general settings, like the language. Well, since we established English in the installation, we have only English here, okay? Well, the maximum size of a history, if we wanted to use CUDA or not, regarding the visualization of the background, and also the visualization or future of the different viewer of the key points and type points, okay? That's the settings part. So we are going to start with File, New Project. We can give here the name of our project. For example, Webinar Project 1. And the path where you can want it to share, save the project. By default, the path project is in Documents, okay, and the folder GRAPHOS. And you can give a description you wanted to give for this project. For example, a main door of the chart, for example. We save it, and now we can start with loading images or loading the video. In this case, are images, so we start loading images. We have to find it in our in our laptop, in our system. I have it here. So in this case, are only 4 photos. You now can see them in the thumbnails panel in miniature, and if we just double click on them, we can see them in zoom in the main panel, okay? And in this case, we don't see properties because I don't know why, but they were deleted. But if we go through the different images here, we obtain the different properties of them in the properties panel. We can see them, this implementation in the next projects, okay? And here, the 4 images in the hierarchical way, okay? So now we can start with the feature structure. Here, as I told you before, we implemented, or it has implemented the SIP GPU algorithms, and these are the parameters of the SIP detector and descriptor of these algorithms. By default, these are the parameters. As you can see, there is established a contrast threshold, automatic contrast threshold, and edge threshold. These are 2 parameters that include these algorithms regarding the image quality of the improvement of the image quality of the images, because we don't have in this software the option of improve this quality before radiometric quality before the process, because we see that with the SIP GPU algorithm, we obtain really good results. It is contemplated here, okay? Just recommend in any case to change only the number of features. Here you see that the image is resampled in order to improve the efficiency of the process, okay? So just let's go to run. Since they are only 4 images, it's really quick, just 3 seconds. We close and we can continue with the next step. But before that, you can see that we can have available now this button that is the future viewer. So we can make the quality control in this viewer to see image by image how many key points are detected, in this case, limited by 5,000 number of key points, and with the site and angle that are the parameters of the SIF descriptor, okay? So we can here check the quality of this process. Then we continue with the future matching process. In this case, as I mentioned, it implemented also a robust algorithm with these parameters that improve the SIF GPU process algorithm, okay? So by default, they are established in the recommendation by the developers, but if you wanted to try to put another parameters, you can do it, okay? So just, I forbidden to mention that the help button is not available, as I mentioned before. So when it is established version, when you put here, the manual will be open, okay? So just run. The matches are done really quick now. And now we have available this button for match viewer. This is really didactic to see by pairs of images the matches, so the tie points, okay? So we can see also image by image the correlation between the points. We can make the zoom, select, okay. And also if you select it, it is selected here again. It's the first one, okay? So we can control if they are okay or not, okay? So this is the match viewer. When we finish with this process, we can go to the orientation process. In this case, we have everything unavailable because the three main options unavailable because it is going to be a relative orientation because we don't have GPS information, we don't have GPS information, we don't have a camera geometric calibration, and we don't have RTK positions. So we just push the button run. And let's see how much time it requires. Hope not too much. It's finished. We can close now. Here we have the time. Also, all these entries in the console are then saved in a log file in the path we established at the beginning. So now we have the first 3D model, that it is the sparse model. By double click on this, we can see here, but it's not really clear. Let's put a bigger point size. We can see the reconstruction and also the position of the cameras. Okay, so in this way, since the self-calibration of the cameras is made automatically, if we again go to orientation, now you see that the fixed calibration is available now. Okay. Okay, so now let's continue with the densification. Densification have three methodologies implemented. The recommended one is MVS, multi-view stereo, okay? And with these parameters. These are the recommended parameters of the developer of the algorithm. And also we are going to, well, if you have a lot of images, it's recommended that the resolution level is incremented, 2 or 3 in cases of a lot of images. Let's say if you have 100 images, or between 100 and 1,000 images, let's put 3 here. Okay, in my case, I'm going to put 2 just in case it closes, because in some test I obtained this result. Okay, that just because I was sharing the screen and we are in Zoom. That's why only. So let's run. It is really fast, but I realized you are in the first exposition of Francesca. I was trying to make some tests, and I see that maybe, I don't know, because I am in the Zoom and I'm sharing the screen and so on, the resources of the system are not efficient now. So, okay, the densification was finished. And now we have the dense model. By double click, you can open it in the main panel. And also, I forgot to say that with the close tab, you can close the images and everything you have open here. Okay, we can put bigger side of the points, and we can see the details of this reconstruction, that it is really good. Okay. Well, we have a relative 3D model, but it is without the scale and without referencing. And in this case, let's see that if we wanted to just scale this model, and now we can do it in this tool. Tools, scale, just establish the distance you previously know of the model. For example, let's say 5 meters is not true. Okay, it's just for testing it. And with this button, you can go to the model and just click by 1 click and 2 click. Well, sorry, 1 and 2. Okay. And we can say, okay, let me scale this one and close. Okay. Now the model is scaled and we can make some measurements. We can measure distances. We can also obtain data from points, but well, you cannot see it because of the resolution of my laptop. But well, here you have the point, the coordinates, but in this case it's not important because we don't have the absolute georeference. So the important one or interesting one could be the distance measurement. For example, from here to here, it says 5.87 meters. Well, let's say it's okay. So we can measure distances, and also with this one tool, angle measurements. So 3D angles. Angles in 3D, okay? You can obtain the area and also the 3D angles, okay? Well, this is the dense model, and we can also make the 3D texture model, okay? So the next step we can select is the mesh. In this case, just well, the reconstruction of the mesh with the parameters of the depth and the maximum solution depth, okay? By default, let's say, it takes more time that I'm expected. So for the next projects, I can open them because I have them previously processed, and see the results. If we see it takes too much time, I can cancel and show you the result. I don't know if the resolution of the screen is the explanation of this. I don't know why. Okay, let's cancel. Oh, let's wait or cancel. I'm going to find the rest of the projects. As you can see, the projects save everything, all the data here in the log. You can see all the items of the console, okay, to check it before or after, okay, and also the results of the orientation, also the sparse 3D model here, and the result of the here of the dense 3D model, and here of the mesh. I'm going to cancel it and well, just open this project and show you, okay? So file, clear story, let's say file, open project. Nothing. I have to close again GRAPHOS and open it again. Sorry. Okay, so open project. And here are the mesh result. Okay. It's an interface really close to the CloudCompare. So, well, something I haven't mentioned, I mentioned how to scale this model, but in case we have a ground control points, we have to go to the georeference tool. And here, but it's a handmade, it's not implemented to import a file, but by handmade, we can just starting to put ground control points, okay, in the images. Sorry, I don't know why. Sorry, now. I don't know what happened with the, something is happening, but it is because of the webinar. It is because of the real-time Zoom meeting. I don't know why, but here we can put the coordinates of these ground control points and then obtain the error of the georeferencing, okay, by putting in this bottom. So I'm going to cancel again, and I'm going to open the rest of the projects I have prepared in order to show you the different scenarios or the different casuistics, okay? So let me check new project, open project. Let's move on to the, I'm going to show you the one of the video, like a new project, okay? So if we have a video, we can load from video. So just find the MP4 format. And now establish how many frames do you want to skip. Okay, so let me, I don't know how many frames we have. Let me put 40 or 30. So set video run. It is extracting the frames with these parameters. If there are too much frames, we can delete some of them. They are going to be too much for processing in live demo in this with these characteristics. So close. I don't have the deletion. I don't know why. No, but not one by one. Sorry. Okay. I'm going to open the project because it's just a frame, like an image that it is taken with the protocol. Okay, so from a video with a protocol, a photogrammetry protocol, it extracts some frames by skipping the others, and then it's the same as you can see in the previous project. Okay, so I'm going to show you the rest of the projects, but just process them. Okay, so in the most interesting one maybe is this one, the full chart with 105 images. In this case, you see, if we click on the images we have here, they see information, okay? So the GPS latitude, longitude, and altitude, okay? And in this case, in the processing step, in the orientation process, now is the fixed calibration, but in the first process, it wasn't available, only the absolute orientation, okay? And well, the result, the MES result is here. As I mentioned, you can you have all the results saved in the path you establish when you start the project, but also you have the option of exporting them, okay? Exporting point cloud or exporting mesh in a PLI format, okay? All of them are in PLI format. In case we have the RTK position, we have to import them in the first step when we load the images here in File, Import cameras is the notation. We have a difficulty because we have different notations from the traditional photogrammetry and the most novelty for photogrammetry, but well, this import cameras tool is for import the data for RTK in case you have it, okay? And in case you have the camera calibration, geometric camera calibration, here you have cameras and you can import, in this case, you can import the main parameters of the camera, the focal, the principal point, and the distortions by a file you have on them, okay? And well, here, well, it is a absolute model, so we can all measure, and it is, of course, georeferencing. In this case, for example, this facade has 7.5 meters. Okay, we can make the measurements we wanted, both in distances or in angles. And this is, for example, an example with GPS information, okay? So now let's move on to the final example that has ground control points. This one is not a cultural heritage example, but it's not important. Just to show you, here you have the images of an urban area, okay? And here the dense model. And you can see that we place some targets in the scenario in order to georeference this model and obtain better results. So it was made in the georeference tool, and also in this case, I don't know why the image is not shown. But this is a problem you can try in your computer. This is not the problem that happen commonly. I think is because of the webinar. Okay, so we have 6 points, but I cannot show you the points by the viewer. That's a pity thing. But well, let me see. I don't remember where I place them, but well, here we have, maybe here in the mesh, we can see them. 6 targets were placed, and then we give the latitude, longitude, and altitude of them, okay? I don't remember where they're placed. Maybe this is one of them, but I'm not sure. In the viewer, in this viewer, we can see each of the 6 points, and we can also move them in case we didn't establish it in a correct way in the first process. Okay, so well, sorry for this inconvenience, because when I test the program, never happens. But well, this is the problems of the lives. And well, to finish, just a slide. Let me show you. Sorry. The last slide, in which I would like to highlight that even we don't have the DTM and also the orthomosaics implemented, they have been developed, and it will be for the stable version of the software that it is scheduled for January, that these functionalities are will be available, and also it will be available the manual of the software. As you have seen in the slide, if you have any specific question regarding the functionality or regarding any problem like the one I have here, the most the best way to proceed is in the GitHub repository. You can establish a new issue, and you need to be synced up in the repository. Okay. And well, additional resources, just I put here a paper of GRAPHOS, even if it is from 2018, because most of the process implemented in the software is here gathered. Even now it have suffered more modifications, and it implemented new algorithms that are not in this paper. So with this, I finish. Sorry for the inconvenience, and well, now let's move on to the questions you have. Thank you so much.
Thank you, Susana. Very interesting presentation and very interesting software also. I can see that a lot of people are very interested in GRAPHOS, and we have some questions, lots of questions actually. So I will try to curate them again as before. Let's see. So there is a very interesting question here. Can you have other projections instead of longitude latitude, such as, for example, UTM?
You mean reproject in another coordinate system? Yeah, yes. By default, if you introduce coordinates, it is established the UTM 30. Okay, but it's something that it is not implemented to reproject in another coordinate system yet. Okay.
So that means that it works in UTM.
Yes.
But what about so the other systems are not yet supported, if I understood correctly?
Yes.
I see. Okay. So I hope that answers the question. There is one question. If maybe you can answer this, can GRAPHOS handle more than 2,000 images?
Yes, we have proof with 700, not more, but 700 images.
So this question, they also said that they already tried to use Micmac to do it, but it take a long time, about 48 hours to do this, while on Metashape it's only around 3 hours. So yes. What do you have any opinion on that?
Well, even I cannot see the potential of GRAPHOS there in the demo, because I don't know why, if it is interrupt because of the live webinar. I don't know. It's the first time I see this problem. It is not faster than Metashape. That is the company's have these best solutions for this, but we have tried to make a reconstruction of 700. This is the most sites project we have with 700 images, and it works, but with CUDA support. Okay.
Okay, important point, the CUDA one. Someone, this is not exactly a question, but this is an interesting remark that says that, so essentially you, with GRAPHOS, we no longer need two different software together because we have something similar to Agisoft and something similar to CloudCompare.
Yes, well, similar to CloudCompare, but just for the to make measurements. Now Alessio is going to extend the potential of CloudCompare. It's not everything implemented, so just some first tools in order to compare or to control the quality of the results.
I see. And a follow-up question is, if I have a 3D scan from a laser scanner, can I put it inside GRAPHOS to scale the textured model on it?
No, this functionality is not implemented. We can go to, for example, we can use CloudCompare in this case and make it in a posterior phase, yeah, in a posterior stage, but not in GRAPHOS.
And then there is another also short question regarding, was the GPS information that you showed in your example obtained only through the settings of the camera? I guess it means if you got it from the EXIF, or how did you get it?
Yes, from the EXIF of the images data.
Okay, I think that is, there is one question that I think is more philosophical here. Someone asked, hi Susana, what sets GRAPHOS different from existing software, and what future developments will make it stand out from other software?
Regarding the advantages, well, it is open source. We can implement the algorithms and new algorithms when we need it, or we can implement different algorithms in order to compare different results, like in the densification phase. So this is a positive point for us and for all of the community, because it is free available. It is open source, so of course you can check the code, the implementation of the algorithms. And finally, the last question was the future lines, and we are trying to implement the orthomosaic result and also the DTM result, so that to separate, let's say, infrastructures from the terrain, to let to only export the terrain, and also to obtain the orthomosaics. So this, together with the manual, is the next steps in the real near close from here to January.
Okay, there is some people asking even twice. Andreas is asking twice. Can we export the point cloud and our textured model from GRAPHOS?
Yes, of course. We can export them. I think I told about it in file, and then export in a PLI format. Okay, PLI format, PLI format. Both texture and the point cloud models.
I see. And I think we'll have time maybe for this one last question. So during your presentation, I did a test with my data and got an error message during the MVS procedure, I think what is meant here. What should we do when we have problems with the software?
Yes, if you have a problem with the software, as I mentioned during the last slide, the best way is to open a new issue inside the GitHub repository. So you have to be synced up, and then you push new issue. I can show you if you want it, but I think in the last slide I just put this option.
Very nice.
Okay.
Yes, I think that's more or less wraps up the question session for you. I mean, you can, if you have the time, maybe you can take a quick look at the Q&A window, and if there is anything that you can answer when you have time, then it would be great. In the meantime, I think we can now try to go to the next presenter. But before that, I would just like to share some information with you. Let me see if I can share my screen. There we go. So I am sharing with you this information since there was also a question regarding this training in photogrammetry. So CIPA is actually organizing a summer school, and it's going to be in Rhodes in Greece. Very nice place during the summer. Also, it's going to be on the 19th, from the 19th to the 25th of May, 2024. So here you have the QR code if you would like to go to the website and get more information. And they also have an Instagram account for the summer school. So go check it out if you're interested in doing a training, a summer school with CIPA. I myself am an alumni of the CIPA summer school, and I can say that I highly recommend this summer school. Anyways, now we can go to the last part of this webinar. So already 2 hours now. So thank you for those who are still staying with us. But we will now go to our next presenter, who is Alessio Ferroni, who is currently a freelance architect, and he is a former researcher at the University of Florence, the GeCo Lab. He graduated in 2017 with the thesis through the reconstruction from multiple sources and reliability analysis of San Gallo's project of St. John the Baptist Fortress in Florence. In 2019, he began his fellowship research with University of Florence and the GeCo Laboratory, focusing on geomatic techniques for the metric survey of monumental buildings. He also participated in some conferences in 2022 and 2023, notably the CIPA Symposium in Florence, and during the CIPA Spring School this year, the week-long workshop in Montecatini, Italy, he was a tutor and assisted with laser scanner data acquisition and processing of the data. And Alessio will be presenting a demo on CloudCompare and how we can use the point clouds that we generate from photogrammetry and get more analysis out of it. Alessio, can you hear me? Or
yes, I'm here.
Okay, so let's see if we can see your presentation. Yes. Can you maybe put, yeah, perfect. Okay, so with that, I give you the floor.
Thank you. Well, first of all, I want to thank every one of you here that is following this seminar and webinar, and thank you all of you from CIPA and ISPRS. And this part of the webinar will be showing the CloudCompare software. For the one who doesn't know anything about this software is software that was developed by Daniel Gerdau-Montin during his PhD in 2003 while working for the Telecom Paris and EDF R&D division. So this software was developed for processing and editing point cloud infos and even triangular mesh data. And to make, mostly, it was developed mostly for making comparison between these two kinds of data. But during the years, this software that I want to remember, it's on open source software has developed, even thanks to outside developers, including other advanced algorithms and specific tools and really interesting tools such as registration and even interactive automatic segmentation and so other machine learning tools. Now I'll go fastly with some slides, just giving you some ideas and tips of what I'm going to present. This is like the homepage of CloudCompare that I'm going to show you later on. But as you can see, it's a really interesting homepage where you find easily, because it's a really nice and open project, where you can have even the wiki page, its own wiki page, the CloudCompare wiki, where you can find also the user manual of one of the most stable version, the 2.6 version. And you will find even on the home page all the tutorials, all the forum, and all the most important things you can go to start on a new software. So for the people that is new to this software, I really recommend to visit it. And to give you an idea of other software, we can, for those who know software on managing data from point cloud, we have RegApp and TrueView from Leica, or all the other software like Trimble. But the fact is that most of the more accessible software, commercial software, are obviously not for free, and since they are not open, while in CloudCompare we have access to the source code. As I told you before, many tools were implemented thanks to the developers. So it's an ongoing project that can be developed more, and while in this one are really close and need to go on editing, you probably have to buy a license and so on. This is to give you an idea. This is the window as you open the software, where you can see it's really easy, and maybe most of you will find it comfortable, since many of the things you have common things to other softwares, like the window of the 3D view, the command toolbars over here, and console on the bottom, where you can see all the operations and ongoing. But what I find really interesting and intriguing of this software is the DB3 window. That is the it's database window where you can see and import all the data and organize your project, because the projects inside CloudCompare are developed like databases. So it's not only editing a single file, single 3D models, single point cloud. We are working on projects that we see how to import CloudCompare projects, singular files, singular triangular mesh, and so on. And we are going to see how to work on the properties of all the single files that we import inside this really powerful software. As I told you before, you can import inside the CloudCompare different kind of files, and most of these files, actually quite all of them, are open format files, such as you can see for the point clouds, ASCII, PLY, LAS, E57. That are most of them are standard formats, so that many of us use. While as for other software that I mentioned before, we're gonna have projects that are developed in proprietary files, such as, just to give you an idea, the recap, we have the RCIS, point RCIS, and RCR. While, for example, we can also, as I mentioned, not only load point clouds, but also triangular meshes, such as PLY, OBJ, STL, FBX, and other formats. Also shape files, and for people who use CAD files, we can see that, for example, as I'm gonna show even in the demo, the open format of CAD files, such as the XF. But continuing on, we can also load rasters, calibrated pictures, and sensors, the TLS, that gives us infos of the instrument we used. And the format file of the CloudCompare, as I'm gonna show you, is the point bin for CloudCompare. To give you an idea of what we are going to see, we are going to see now during the demo some easy infos of tools of navigation, how to clone, merge the data that we have inside, how to sample, cross sections, so how to have some profile info, how to segment the data that we have, and noise removal and scalar field. For example, now I'll show you the difference between different kind of data that we have inside, and how to. I started with the raw image. You can see we have raw laser scanner data, E57 laser scan data that I added with all the full data, and I have quite a billion points. And the difference that I can see between the one at the right is that we have less data, but I halved somehow the amount of points. And mostly what I want to show is that in order to work on our data, we should think about how much we want to our machines, our PC, to work on our data. Because if I start with a file, this was really little, not such much high size data, but with the subsample tool, we can see that we still have good quality info. We still can see it's a door, an important monumental door, but I just have to adjust our quality, and we still have a good cloud, but with less data. So our PC will thank us for this effort. And this is, for example, as we can see, we can make some operation with segmenting clouds and also removing some noise. This is two sections that we have from the laser scan data. That in the one on the left, we have a really noisy laser scan data, while with some simple tools we can easily make it more readable. And one of the tools that I told were implemented afterwards, the launch of the first release of the CloudCompare, is the registration tool. That it's a really powerful, important tool. And in my demo, what I want to show you is how to work on a registration made by starting by data coming out from a control network survey. So what we have at first is a list of points that are gathered from control network survey. So we know that all of these points are points with a coordinate system that we want to use as our reference system. So we want to register inside our system another point cloud that it's a raw point cloud that we want to log to this and align to this system that is the control network system. So this operation means to give pairs of points from the control network survey that inside this program, I'll show you, that will be considered also as our point cloud data, such as the laser scan survey. But we taking these pairs of targets, we're gonna mesh them in order to gather the same coordinate system for both of the data. That's going to be the our project. So this is going to be our last the result that we want to obtain, where we have all these points that were taken from the control network survey and the laser scan that is perfectly aligned with targets and so on. But this is not the only tool for registration. There is another tool called ICP, that is interactive closest point tool, which we can see how even if we don't have targets, we can somehow try to finally register these infos and align them correctly, or as much possible we can do. A reminder, we can do the same operation not only with point cloud data. We can do the same exercise as I told you, mentioned before, the one choosing the pairs of points, and also this one, the ICP tool. We can do it not only with point cloud, but also with meshes data. But other tools that I want to mention, for example, are some tools that the software gives us. Even we see that inside this software we have a lot of interesting plugins. And one I want to show you really fastly is, since we mentioned it before, like all machine learning softwares, In this one, we use the Canupo plugin. That it's a really interesting tool that works as an interactive machine learning, where by choosing an object that we want to classify, in this case is I wanted to classify vegetation inside a small area. This plugin finds how this data that we somehow isolated, like the tree, acts and behave in our coordinate system as a geometry, as values of color, and scalar fit in sense of intensified color. So this plugin somehow find the difference, the gap between two different clouds that can be, as I can show you here, that it's our first cloud of a wall of, this is a wall of the fortress in Florence, the Basso fortress. So how the cloud in the wall of this fortress is a certain kind of geometry, really close to a surface, while the vegetation, it has a volume, the cloud, and it has a different color, different shape. So how it behaves three-dimensionally. And by doing this classification, we see how the plugin here, we activated it and detects the different kind of vegetation inside our project, and split it in walls and vegetation. Where the wall, or what is a surface that behaves mostly as a wall, is highlighted in blue, and what it looks and seems to be vegetation, it's red. So it is, once they are separated, it's really easy to separate the two data, vegetation and wall, and to obtain, for example, what was our aim, just the simple and flat data of the walls. For the demo, since we introduced before the upcoming symposium of this year, I'm going to use some of the data that we used during the CIPA Spring School that was held in Montecatini Terme this year, so in Tuscany. So it's data that we took from the workshop, where the students, let's say, what they did was to take data from photogrammetry, from terrestrial laser scanner, and also did a control network survey. This is a previous control network survey that we have done before the CIPA, but we during this workshop we obtained a new control network survey and took some other scans with terrestrial laser scan. And so I'm gonna show you how to use some of these tools by using the same data that also our students used for during this workshop. Okay. So what I want to start from actually is just to showcase, like, showing you here the database of CloudCompare, that we can see where and how we loaded meshes, and where we can somehow see we loaded point clouds. So in the DB3, we have all the project that is the point bin format, as I told you before, where I loaded in this one previously a mesh, since it's really a really defined mesh. Now I'm gonna highlight just the mesh inside. This is a mesh that was gathered by photogrammetry. As you can see, we have even some photogrammetry targets inside. And it's a really powerful tool, as you can see, CloudCompare, because if you can see, this is a really heavy mesh. We have 7 million and more, quite 8 faces. But if you have some data that is coming up from photogrammetry, that it's only in it's only a mesh. This was an OBJ format, for example. For example, what I did, I wanted to make it inside some operation, and what I did is to simplify the mesh, making it a point cloud. As you can see from this icon, we see that this one is a triangular mesh, this one, and now I'll close it, switch it off. Now we have a point cloud data, because inside CloudCompare we can even make some interesting operation that I cannot. Yeah, where we can sample meshes, making that point, so a cloud, a point cloud, where we can choose, for example, the final result. So, for example, we can have from our 7.8 million faces. If we use this tool, we can transform these 8 million faces into a point cloud of above a million points, or choose to work on the density, where, as you can see, I wanted to keep infos of color information, and texture. So the point cloud, as you can see, kept the infos, and we have this data that it's sampled. It's, as you can see, a million points around, and I did this in order to make some operation as sectioning, making other sections where I wanted to gather some profiles of these statues. This is a similar project. As you can see, still we have a statue. What I did is just to make this triangular mesh another sampled point cloud, and what I did is to make some section of some of those parts, like base of the column, the base of the main statue, that is this one, and all of these infos can be used to be, for example, exported as cloud data but also other kind of format file, such as E57 as point cloud. We can gather back again some DXF if you want to work on CAD, or as I wanted in this case for other software to make some cross section like in Geomagic, the apply format. To show you how I worked on this on these files, I can show you that, for example, the import export. So if I want to import here a project, we can see that the CloudCompare entities, the point .bin is the format that we use for projects inside CloudCompare, and that is this main folder that is as the name says, is a 3D database. So everything that is inside these three organization will be inside the final bin file. But if I want to make, for example, a copy of this and put it, want to no, sorry, I want to for example, load E57 inside. Want to load this one. Too much heavy probably. Sorry, I have to close it because I loaded the wrong one. I try back with this one. For example, I'm going to showcase another example. This is the data that I told you before mentioned from Montecatini. And I'm gonna showcase directly here what I wanted to show you. So I'm gonna load two E57 file. Now I'm gonna load this one. It's a scan that comes from one singular position of a terrestrial laser scanner. So as we can see, as I loaded this, I loaded, as you can see from the DB3, different file. So when I'm going to save this project, it's going to save everything that is inside this project. So every time I import something inside, we see a folder containing the the singular data. But we can also add this data if we want to make all a singular project, so a singular database, where we can contain in each folder all the data of these folders. So I'm going to switch off the data of the other that I showed you inside the folder. This is the raw laser scan of a singular position, as you can see even from this whole inside. What we have here in this folder is the point cloud with, in the properties, we can see all the infos of this raw scan. As you can see, it's really heavy, about 40 million points. What we can see, this is really important inside the properties, is the color info of this terrestrial laser scan data. That can be an RGB, so colored laser scan. But on the scalar field, we can see and how it works in the intensity of the data that we obtained from the laser scan. In these properties, we can also see information about intensity and the other scalar field. Now we see how scalar field works. So how many of them are active, and we can choose in the coloring of the scalar field which kind of coloring we can give to the laser scan, like blue, white, red intensity, and work on which kind of intensity data we want to work on. So as you can see, this is the, if I use, for example, blue, white, red. For now, you see that we have just a few data on the range of red intensity, but a lot of data coming out from the blue one. And then we see how to work on these values. I go fast even because time is going on. And in order to make this data not so much heavy, we are going to use the subsample tool. This subsample, the sampling, we can set it by distances between the two pairs of clouds, but we can even choose random. So just to choose how much are going to be the remaining points, and so on. So to give you an example, this is data that I loaded before. We have a point cloud here that I sampled with a distance of 5 millimeters. And this is the full raw laser scan loaded inside. And as you can see, I don't know if you can see the difference, but here we have even a target. Some of the things we are going to work on, like targets, since the data that we had before is really good, I still want to remember about 40 million points here, and in this one, by clicking, I'm choosing the other data. We have now around 7 million. So we still have a lot of data, and data it's still readable. And as you can see from the files, about 1 giga of data in one, and just 5 times less the second one. So it's really important when we are using really important data, as in terms of amount of data. So continuing on, in this file, now I'll show you how I imported inside CloudCompare the survey data that we took from the during the control network survey. This is a TXT with some coordinate infos of targets that are the ones that I showed you before. For example, this one is the should be here. We have one. Clicking. We should have one that is the this one is not really readable, but 2033, for example, that is one of these one that we have some coordinates. So what we want to do is to log these point cloud to our coordinate system that that we already somehow gather. So from the control network survey we have here we have the tools for picking information, so point picking, and we can see here that we can select points and make some operation. As you can see, we have infos of coordinate system here that are really different from the ones we gathered during the control network survey. So we want to log the point cloud to our coordinate to our control network survey. In order to do that, what I did is to use the TXT file that where we have the coordinate system of each point, and we can use every kind of CAD tool, CAD software, just in order to make some points that must be in the coordinate system that we have. So as you can see, this point must be the target I showed you before, the 2033, because it has the same info of X, Y, and Z in the X, Y, Z axis. So once we have this CAD, we just export as a DXF, save as a DXF, so that in this way we have the chance to import, as I showed you before, these points inside CloudCompare. I'm gonna show you even this, that in this case, when we are using objects that are really far from the actual coordinate system, you could ask us, do you want to to shift this data to a more approachable coordinate system or closer to the one we are using. In this case, obviously not, and we just say no. So now we have these points, as you can see, are the ones that I just switched off. The only thing I've done here is I gave them some label. I labeled them just by using the pick mode, as I showed you before. Here you can see the pick mode, where we have infos in coloring and coordinate. And also we can save the labels on them, just like the value of the target. So target 2033. To go fast, I'll go back to the ones we already have. So okay, now I have some issues with the visualization. Sorry. Okay. So as you can see, these are the points that are labeled, and this is our laser scan, so our laser scan data, and we want to match these pairs. So in order to do that, we are going to use the align to clouds by picking, where we decide which is the entity that we want to align to. So the reference is the point, so the one coming up from the contour network, and we have these this table. I'm sorry, but I have the zoom command even that are on my window that are really annoying. So we choose directly inside inside the so this inside the laser scanner point cloud, the points that we want to pair. In this case, I by mistake I clicked on not good point, but let's say this. I'll be really fast doing this operation. I'm sorry. But as you can see, this one is going to be on the reference entities. So the one that is going to stay still. I'll go and check for the 2033, for example. So another point, and I'm going to pick another point. It's going to be, for example, this one. Actually, what I had to do is to check if I could I don't see the other, can't even move this one. So this is the other data from the other scan that here we are. It's really annoying because I cannot move the tool here, this bar, but I can pick those three points. Hoping I took the right one. That should be the. We should remember the first one I picked. That should be the 2029. And so A0 matching with the R0 point, the R1 to the 2030 target, and R2 to the 2033. We could take another point, but in order to make other operation, such as adjusting the skateboard, since laser scan data doesn't and control network survey data doesn't need to be scaled because they are in the same dimension, we just align them, and as we can see, the rototranslation operation just happened. We can, if we want to be want to check the quality, we can try to make it better. For example, we can see that we have some terms in kind of error. I was really fast because it's really time is really running out. So I'm sorry, but usually if you do it precisely, you gather really small errors in order of centimeters. Here we are really far from a good quality registration, but I wanted to showcase mostly the let's say the tool and how to go with the process. So I'm fine with this, and we can see even the rototranslation matrix. We can even, if we want to go back, there is a tool where we can reverse the matrix, so we can have the two data back again to the original. Because something I didn't mention is this. This is a destructive process. So once we moved the laser scan data or the data that we want to move and to register, we cannot go back unless, as I told you, we reverse the matrix that we can even find in the console. If you can see, we have some numbers that are the corresponding to the matrix, and we should find it even here on the transformation history. So this is just a tip. To be really fast, I want to show you even this one. That is some operation with the translate and rotation. We can try to fit as much as possible these scans over there in this way. So these are two different laser scans, so from different position. And with this operation that is automatic, so it will take really 2 seconds. What I want to show you is that with this tool, you can, this tool tries to match as much as possible automatically these two scans. And in order to do this, it finds comparing points. And what I recommend is to use low overlap percentage, and it makes a certain number of iterations in order to find the comparings. And as before, you have to choose which is the one that we want to align and which one is the reference. So I'm going to do the ICP. So it's going to process. And just as before, now it's still working. And just as before, it didn't work well. Maybe I just try to make it more easy. Okay. I'll just pause it a bit. Okay. And as before, what I want to say is that here it worked, as we can see, even the results are even better than the one before, where we have a really small percentage of error. Because what it needs is to have as much possible comparison of points. And what we see is that somehow automatically we have registered point cloud, where we have even some information on the scalar field of the one that we moved. So I want to show that, for example, if we want to make cloud distance, because I think maybe most of you want to see this, it's that we can try to see how much is the distance between the two clouds. And I want to see the difference in the X, Y, and Z components. It's gonna take it took really seconds last time I did it with the same. I am sorry, I don't know if it's because of the Zoom meeting, maybe it's
Maybe while you let that run, we can get the Q&A started, just watching the time.
yes, sorry, no, I didn't hear because I had to move the Zoom bar on the clock. Sorry.
All good, all good.
I'm sure I was really running out of time, but not so much. I'm really sorry.
That's okay. No, that's okay. Yeah, I guess that's a good idea because I can already see some questions, and I guess some of the questions maybe you can answer shortly. So
Yeah.
there is a question, for example, regarding the sections that you created for the objects. So I think you showed how to create some sections before. How would you then turn them into cross-section vectors?
How I can make some of these sections. For example, the tool is we can have some tools like the cross sections here. It's not working at the moment. I'm sorry.
That's okay. I think it has to do with also the bandwidth because you're also sharing your screen. And...
Try to see if I can use the other one. CloudCompare. Maybe this one is working. Okay. Maybe it's not so much heavy. Okay. Okay. Looks like it works. Okay, but I don't want to use this one. Sorry. Remove this one. Okay, so I'm gonna use this one that it's just not so much heavy. So this tool, we have the chance to make some bounding box of our object, where we can decide to make some slices and export this section. So while dragging these arrows that are coordinate arrows, we can size our bounding box and decide to extract. In this case, I want to extract this slice. I don't know if you noticed it. It already made a slice, this one that is highlighted. And we can even make more slices, and it's adding new slices. But you can make even multiple slices, like where we can define the length and how many of them we want, what we want to extract, if it's any info we want to gather from the, how we want to repeat this operation, the Y or the Z or the X coordinate, for example. And as you can see, these are the slices that we just obtained. And we can save them and extract info just from them.
And so the question actually also mentions if it is possible to turn the cross sections into vectors.
I never tried. There are some tools where you can use actually, as I know, where you can extract polylines from this, but I never tried. I usually did the opposite, extract points as a data to start as the XF mostly, and then turning it on other software. But as I know, I never tried.
I see. Would you like to finish the cloud-to-cloud comparison that you did before?
Let's see if it worked. I don't know if I have some. I see that it worked, the scalar field, but since I have the other tool working on, I cannot show.
Maybe while we wait, there is also a question that I think is quite interesting, if you can answer it.
Okay, now I have it. Maybe. No, it crashed.
Oh, that's too bad.
Oh, let's see if I. On this one, it won't work. Sorry, I don't have it. Another one loaded. Yes. Maybe I can launch it one right away and wait it finish.
Sure.
Okay. I'll try to answer while I'm attending the other question, maybe.
Yes. So maybe we will only have time for 2 more questions, I guess, since we are at the end of the scheduled time for webinar. So there is one interesting question here. So using CloudCompare, I have difficulty in exporting geo-referenced mesh. I tried to export in PLY or OBJ format and open in Metashape. However, the mesh shape becomes irregular. I think there is a problem with global shift, but I don't know how to fix it. Do you have any opinion regarding that?
Could be as the message that I mentioned before. maybe during the export, as I shown before here, if I try to load, for example, on this one, that it's on a completely different coordinate system. I try to load the data of control points. In this case, it didn't show me the message, but it asks you about the global shift. So it has to be unchecked, that part, because usually it happens during the import. Never had the message in the export, but could be this, that it demands you to shift to a more closer reference system.
Okay. And maybe one last question. I think this is an interesting question. Hi, according to your experience and knowledge, what have been the updates regarding the use of CloudCompare together with artificial intelligence, if there is some?
Well, the tools that I mentioned before is, for example, the one that is a machine learning tool. This one is called Canupo. That is one of the plugins that you find in the right. But let's see if I keep highlights. That is, for example, automatic segmentation. There are many other plugins that are being developed. And one of these is, for example, the one I showed before, where by using this plugin, you can make classification, automatic classification of the data, point cloud data. So you can, I showcase just the example of the wall and the vegetation, but as I know, there are other tools, for example, that were developed by a university in Scotland to automatically detect gravels inside a wall and to have the a correct border of the gravel inside an ancient wall, for example, of a castle in Scotland.
Thank you. Actually, there is just one more question regarding CloudCompare that I see here, although maybe I can read the question to you. Hi, is it possible to do a diagnosis of parietal paintings using this technology? So about the consolidation parts that needs consolidation, things such as that.
But it depends. If it worked, I wanted to show somehow the scalar field detection, the comparison of the two clouds, because before, unluckily, it all went down. I see if I can make it really, really fast. But if I move them together, try to make really fast ECP. But I don't know if I'm going to be in time, but I'll see that I have I'll see the colors of the lasers of the data of the laser scan, that it will be colored by a scale of distances. So I think that for sure the answer is yes. I mean, I would use it for sure, because there are many values that that you can make comparison on CloudCompare, because you can make you can choose to have your values of colors of coloring of the laser scan data in distances, values of temperature, of normals, and all of these values are easily detected using this tool.
Okay, well, thank you for your answer. So unfortunately, we don't have a lot of
I'm sorry,
time remaining, but that's okay. I think it's a technical issue, but I hope the message comes across to the participants on how to do the operations that you mentioned. And I suppose we also said that there is a link to the documentation of CloudCompare. There is even a wiki, if I'm not
yes,
mistaken.
we have on the home page, we have all the infos about documentation. So we have here on the documentation page all the manual that is available in the English version or French version, but also we have the wiki page, also the plugin wiki page, where we can see the Canupo, for example, plugin. That is the one I wanted to mention before, for how to use machine learning for detecting and classify point clouds. But also, this is the download page where we can see that the one I used is the stable release, the 2.12.4 Kiev version. And also there is the GTAP with the source code. So for all the interested developers, you can find the source code of CloudCompare.
That sounds great. So I guess people who have questions can also ask you by email maybe, or also consult the website for the documentation.
It would be a pleasure.
So yes, so I think that's it. So I would just like to finish with one slide. Yes, so again, thank you everyone for attending this webinar. Again, this was organized by ISPRS Commission 2 Photogrammetry Working Group 6, Documentation and Data Acquisition and Processing for Cultural Heritage, with the help of CIPA and CIPA Emerging Professionals. So big thanks to Joe and Michelle from the CIPA and CIPA EP, and also to the speakers, Francesca Matrone, Susana Del Pozo, and Alessio. It was a very interesting webinar, and I really hope that the information would be helpful for our participants. As we mentioned before, the video will be recorded. It's recorded, and we will share them through the YouTube channels of the ISPRS and the CIPA Emerging Professionals, and we will let you know about the links in the chat. And with that, I would like to close this webinar, and thank you again, everyone.